Hello friends, class 11th chemistry. We were discussing unit 10, the S block elements, and in this video we will discuss about chemical properties of alkali metals. The alkali metals are highly reactive due to their large size and low ionization enthalpy. The reactivity of these metals increases down the group because down the group size is increased, so ionization enthalpy decreases. Reactivity towards air. The alkali metals tarnish. Tarnish means their appearance become dull in dry air due to the formation of their oxides, which in turn react with moisture to form hydroxides. They burn vigorously in oxygen, forming oxides. Lithium forms monoxide, sodium forms peroxide, and other metals form superoxides. The superoxide O2 minus, okay, O2, not O2 negative charge. Charge is only one negative on two atoms of oxygen. Is stable only in the presence of large cations such as potassium, rubidium, and cesium. Dear student, as per the lattice enthalpy consideration, larger cation form the stable compound with larger anion. Okay, and smaller cations form the stable compound with the smaller anions. So in this way, these potassium, rubidium, and cesium, these are larger in size. So they form stable compound with superoxide ion. The reaction can be represented. Lithium, when react with the O2, mainly it will form lithium oxide. When sodium react with the O2, it form sodium peroxide. Mainly, some amount of sodium oxide is also formed. The same way, potassium, rubidium, and cesium, these are represented by capital M. When react with the O2, they will form MO2, superoxide. Lithium shows exceptional behavior in reacting directly with nitrogen of air to form the nitrite Li3 and lithium nitrite. Because of their high reactivity towards air and water, they are normally kept in kerosene oil. Now there is one question, problem 10.1. What is the oxidation state of potassium in KO2? That is potassium superoxide. The superoxide species is represented as O2, one negative charge. Since the compound is neutral, therefore the oxidation state of potassium is +1. Reactivity towards water. The alkali metals react with water to form hydroxide and dihydrogen. Reaction can be represented like this. This M is the alkali metal. When react with the water, it will form hydroxide, this OH minus ion, along with liberation of H2. Reactivity towards dihydrogen. Dihydrogen means H2S. The alkali metals react with dihydrogen at about 673 Kelvin, but lithium will react at 1073 Kelvin to form hydrides. All the alkali metal hydrides are ionic solids with high melting points. Reaction can be represented this M plus H2, and this is metallic hydride, which is ionic in nature. Reactivity towards halogens. The alkali metals readily react vigorously with halogens to form ionic halides MX. Lithium halides are somewhat covalent. Now what is the reason? It is because of the high polarization capability of lithium ion. The distortion of electron cloud of the anion by the cation is called polarization. The Li plus ion is very small in size and has high tendency to distort electron cloud around the negative halide ion. Dear student, if you remembered Fajan's rule, Okay, smaller size cation can polarize larger size anion. So more covalent characters will be there. More polarization, more covalent character. Since anion with large size can be easily distorted, among halides, lithium iodide is the most covalent in nature. Reducing nature. The alkali metals are strong reducing agents, lithium being the most and sodium the least powerful reducing agent. Actually, this reduction power is represented by the standard electrode potential. Okay, this table gives the value of standard electrode potential of alkali metals. Okay, just see, for lithium this is most negative, and for sodium this is least negative among these alkali metals. So lithium is the most powerful reducing agent and sodium is the least powerful. And actually the standard electrode potential represented as E naught, which measures the reducing power, represents the overall change. This, that is, metal in solid state when converted into metal in gaseous state, sublimation enthalpy. Metal in gaseous state will convert into metal ion in gaseous state, ionization enthalpy. And this is metal ion gaseous state when converted into metal ion in aqueous state, hydration enthalpy. Okay, the overall result of these enthalpy determine the standard electrode potential. Okay, more negative standard electrode potential, it means more stronger reducing strength. Now if we see the value of lithium, for the lithium the ionization enthalpy is maximum because of the smallest size of lithium among alkali metals, but still it is powerful reducing agent because lithium ion, that is Li plus, is smaller in size, so its hydration enthalpy is highest. So we can say with the small size of its ion, lithium has the highest hydration enthalpy, which accounts for its high negative E naught value and its high reducing power. Okay. Now there is one question, problem 10.2. The standard electrode potential for Cl2 oblique Cl minus is plus 1.36. For I2 oblique I minus is 0.53. For Ag plus oblique Ag, this is plus 0.79. For Na plus oblique Na, this is minus 2.71. And for Li plus oblique Li is minus 3.04. Actually, all these represent the redox couple. Okay, and to determine the electrode potential, all we can say reaction is always represented in the reduction form. Okay, so if we say this is Ag plus, then this will gain the electron, then this will convert into Ag. For this, the reduction potential, or this is not the standard electrode potential, this is given for this. In the same way, for this is Cl2 Cl minus, we can say this is Cl2, when gain the electron, this will convert into Cl minus. Okay, so combination, we can say this one is a reduced form and this is oxidized form. If oxidized form and reduced form are separated by this slash, then this is known as a redox couple. Okay, so for different redox couple, standard electrode potential values are given. Now question is, arrange the following ionic species in decreasing order of reducing strength. Now just compare these values. For any redox couple, if standard electrode potential is more negative, or we can say less positive, its reducing power will be more. So for the if we examine carefully these values, we can arrange these species in the decreasing order of reducing strength like this: Li, then Na, I minus, then Ag, and this is Cl minus. Clear? Solutions in liquid ammonia. The alkali metals dissolve in liquid ammonia, giving deep blue solutions which are conducting in nature. The reaction can be represented like this. This M, alkali metal, and this is ammonia. Its X and Y moles are reacting, and these species are formed. This is electron, okay, and ammonia in this is a solvent. So the blue color of the solution is due to the ammonia-tate electron. This is ammonia-tate electron, which absorbs energy in the visible region of light and thus impart blue color to the solution. The solutions are paramagnetic. Now, what is the meaning of this paramagnetic? That is, attract towards external magnetic field. And any substance is paramagnetic due to the presence of free electron, due to the presence of unpaired electron. Okay, and on standing, slowly liberate hydrogen, resulting in the formation of amide. This is M plus. This is AM. This represent the ammonia. Okay, this is ammonia-tate metal ion. This is electron, and finally we will get this metal amide along with the liberation of hydrogen gas. In concentrated solution, the blue color changes to bronze color and becomes dimagnetic. Dimagnetic means slightly repelled by the external magnetic field, and this is due to the absence of unpaired electron. When concentration is more, the electrons get paired. So the highly concentrated solutions show diamagnetic nature. Usage of alkali metals. Lithium metal is used to make useful alloys. For example, with lead to make white metal bearings for motor engines, with aluminium to make aircraft parts, and with magnesium to make armor plates. Lithium is used in thermonuclear reactions. Lithium is also used to make electrochemical cell. I think you are familiar with lithium ion battery. This is used in the mobile. Okay. Sodium is used to make a sodium lead alloy needed to make. This is tetraethyl lead, ET for ethyl, C2H5, and PBMe4. This is tetramethyl lead. Okay, and actually these organo-lead compounds were earlier used as anti-knock additives to petrol, but nowadays vehicles use lead-free petrol. Liquid sodium metal is used as a coolant in fast breeder nuclear reactors. Potassium has a vital role in biological systems. Potassium chloride is used as a fertilizer. Potassium hydroxide is used in manufacture of soft soap. It is also used as an excellent absorbent of carbon dioxide. Actually, carbon dioxide is acidic in nature and potassium hydroxide is basic in nature. And cesium is used in devising photoelectric cells. Okay, thank you. Subscribe my channel to get next video from this chapter.